Holding. Okay, so we are on. Today we are going to continue with chapter 19. We're talking about section 3, and that is the strength of acids and bases. Of course, last time we talked about his Judy. I was calling you because I didn't find anybody. I was thinking of going back to the office. Okay, good. Judy is here. All right, so we talked about the acid and bases theory last time, and we explained that there are 3 of them. They are Arrhenius and okay, the Arrhenius and the Brewster-Lowry, and then we have also the Lewis acids and bases. And then we talked last time about the let me just bring this back. What's wrong with this? Okay, so last time we talked about the pH and how to determine the strength of the acidity of the acid by measuring the hydrogen ion concentration. We talked about the pH and talked about the relationship between the hydronium ion and the OH minus. Today we're going to talk about the strength of acids and bases. How can we decide what are the factors that we are going, or the properties that are going to be used in order to determine the or to classify the acids and bases as strong or weak. Yani, if we want to classify students as being good student and weak student, or strong and weak student, usually we look at their grades. So that is the property that we usually use in order to discuss or to to decide about their strength. Now, in the case of the acids and bases, we look at some other properties in this case, which is the degree of dissociation. Anyway, let's take a look at this question in the picture. This is lemonade, for those who like lemonade in the morning. What makes one acid safer than another? I mean, in lemon juice contains citric acid, and the pH of that is 2.3. So that should, and that is yet, it is safe to consume. While if you take a couple of drops of hydrochloric acid, that might, hurt your mouth or your throat and might cause you a lot of problems. So what is the difference? Why this is safe? Why the other one is not safe? That is what we are going to do today, which is look at the degree of dissociation, or how the acids are dissociated. So, because last time we talked about ionization of acids by giving an H plus and an ion which is left after that. So based on the degree to which ionizes in water, يعني, if we have, for example, let's say, this has a problem, the right. Let me just restart this and we'll see. Just going to turn it off and turn it on again. Hopefully that will work. Okay. Still the same problem. Anyway, so we're talking about based on the degree at which they are ionized in water. If you consider hydrochloric acid, which is HCl, when you put it in water, all of it, all the acid that you put in there will be ionized into 100% of that will be ionized into H plus and Cl minus. Of course, H plus is going to show as H3O plus, which is the hydronium ion. That's something we talked about. So strong acid are completely ionized, and weak acid will be partially ionized. An example on the strong acid is hydrochloric acid. If whatever amount of hydrochloric acid you drop or you add into water, then that will be dissociated or ionizes into H plus and Cl minus. All of it, 100% of it. While if you consider one of the weak acids, like ethanoic acid, for example, that is this one, or acetic acid, that is the common name for that. Acidic acid, CH3COOH, if you put it in water, only 1% of that, even less than 1% of that will be dissociated into H plus and CO2. So that's why we have a kind of equilibrium, as you can see over here. So this one will exist, this one will exist, and that one will exist all at the same time. While in the case of the HCl, where we have HCl dissociated into H plus plus Cl minus, this will be 100%, so this will be over. No more HCl will be found in there as HCl, but all of it will be converted or will be ionized as H plus and Cl minus. While in the case of weak acid, you're going to see that less than 1% of that will be dissociated. These are some of the strong acids and bases that are known. Okay, that is the Faisal Hussein. He said HCl is more acidic. Usually we don't use this kind of languages, which is more acidic, because more acidic doesn't mean that it's stronger. And I will show you this toward the end of this lecture. Usually we say it is stronger acid than others, rather than strong acid and weak acid. Strong acid, yani it will dissociate by or ionize by 100%. And if it is a weak acid, it will ionizes but by small portion, which is partially like 1%. So here we have hydrochloric acid, nitric acid, sulfuric acid. These are considered as strong acids. Okay, so strong acids means that they will ionize in water by 100%. While if you consider phosphoric acid, ethanoic acid, carbonic acid, hydrochlorous acid, all of these are weak acids, which means that part of that will be dissociated or ionized and the other one will remain. The same thing applies about the bases. Some of them are strong bases, like calcium hydroxide, sodium hydroxide, potassium hydroxide, while ammonia and sodium silicate are considered weak acids, weak bases. Okay, now to understand it better, and I want you to focus here. This is the most important figures that you will see in this section. We will have to get back to this later on in our calculations. So I want to make sure that you understand this. So let's take a look at the first one here, the HA. HA means an acid, regardless of what that acid is. If it is a strong acid with a complete dissociation, all the green will be changed into these two, purple and pink one, which means that for example, HCl, all of it will be converted into H3O plus and A minus, which is Cl minus in this case. So you can see that from the size of this one, okay? If you look, that's the problem with the pen, and this one as well. So the sizes are complete. This will completely gone, and we're going to have one this. The other thing is that these two are equal. So the concentration of the A minus or the Cl minus in this case, and the concentration of H plus are equal. And they are equal to the initial concentration of HA, which we started with. Why? Because this is 100% dissociation. Now, if you want to consider a weak acid, which is like this one over here, when it is little dissociate, it will remain. See here, there's nothing green in the product. While here, it will remain only small portion of that, which is this part over here. That pen is a disaster. So that portion over here, if you take one of those, you can put it up here. It is exactly equal to the something that is missing from the green. Okay, so at equilibrium, after we put acidic acid in water, we're going to have three components in there. We will have the HA, which is the concentration, the initial concentration minus whatever dissociated, and the dissociated one or ionized one, the negative and positive are also equal. Okay, this is very important later on for our calculation. In this case, in the strong acids and base, the HA will completely ionize, and you will see the purple and the pink, they are exactly equal in the concentration equal to the green one. While here the green is only less by whatever being ionized, like for example 1%, 2%, 3%, 5%, and that 5% is shown in here in these small ones. Okay, so that's the graphically how you understand the strength of acids and bases, and which one, how the strong one and how the weak one are treated. All right, now when we have an equilibrium, in case of the strong acid, there's no equilibrium. We could say that the reaction goes into completion. Yani all the HCl being converted into H plus and Cl minus. In the case of the ethanoic acid, we're going to have an equilibrium between the acid itself and the H plus and the ion, which is CH3 or the acetate in this case. Now, we can write something called the equilibrium constant. What is the equilibrium constant? It is the ratio between the dissociated form concentration divided by the undissociated form. Yani we have the, here we have the K equilibrium constant is equal to the H plus concentration, the A minus, which is in this case the acetate, divided by the initial equilibrium concentration of that. This one here is the green one, which is left after the dissociation. And that is the water concentration. Now, the water concentration is always constant because that's plenty of it. So if we move this water concentration, if we multiply this by water concentration and multiply this side by water concentration, then we can cancel it from here. And then we're going to have in this side, K equilibrium multiplied by the water is equal to the H plus plus the other one, which will look exactly like. Today the screen is not helping me, but anyways, can move it from here. And sometimes it works good, عشان أكون fair. So that multiplication of K equilibrium with the water thing is equal to something we call it Ka. What is Ka? It is the acid dissociation constant, they call it. Acid dissociation constant is the ratio of the concentration of the dissociated form, which is these, the small little purple and pink ones in the graph, divided by, and of that of the acid concentration undissociated form, the one which is left, the green, the short green. Yani, what we have, if we go back, I want to take you back to this figure. That's the problem. It moves always forward, regardless of whether you push the forward or the backward. So we're talking about these three. See these three over here? So we're talking about, why it's not showing here? Move. Okay. So what we have in that equation is basically this ones. The dissociated ones divided by the undissociated ones. That is what K is about. All right. So if that is the case, then how can we calculate the Ka for any acid? If that is the case, if Ka is basically equal to the H plus times A minus divided by the equilibrium concentration of that. So all what we need is the initial concentration. If we have the concentration that we started with, how many or what we added into the water, how much ethanoic acid we added. In other words, what is that big green that we started with? If we know the big green, right, then these two are equal. And one of them is the H plus. And H plus we can calculate it by measuring the pH. So this way you can determine that. Let me just explain this to you again. تعبت وانا جايب الكمبيوتر هاي. Okay. All right. So acid dissociation concept reflect the fraction of ionization. That is an ionization constant. If the degree of ionization is large, which means we are talking about a strong acid, then the Ka value will be larger, right? Because Ka is equal to the dissociated form, concentration of dissociated form divided by the undissociated. Now, in the case of a very strong acid like hydrochloric acid, the undissociated is zero because all of it has dissociated. So if you divide something over zero, that will be infinity. So there is no Ka value for strong acids, but there are K value for weak acids. Between them, يعني, if we have a student here in our class that is getting 100% their course, he's the only one, okay? So that one does not have a K. There's no way that we can judge him. He's the best. He's getting everything full mark. While the other students, if we consider them as weak students, but they are not the same. One of them is getting D, the other one is getting C, and the other one maybe A minus. So depend on the degree of dissociation or depends on your grade. So weak acids have small Ka values and stronger acids. Now, when we say stronger, doesn't mean that we say strong acid, stronger relative to each other. Yani among the weak acids. So all the weak acids, they have Ka values. Among them, there is something strong and something weak. But we're not talking about the very strong acid because those are the one which does not have a Ka value. Here's an example. Read this very carefully. It says here nitrous acid, which is HNO2, has a Ka value of 4.4 times 10 to the minus 4. Right? But ethanoic acid has a Ka value of 1.8 times 10 to the minus 5. What does that mean? I mean, what you can read from this, how you can interpret this. I've forgotten the microphone for mobile. Okay, so how can you read it? This means that nitric acid is more ionized in solution than ethanoic acid. In other words, nitrous acid is a stronger acid than ethanoic acid, although both of them are weak. If we compare these two to hydrochloric acid or nitric acid, they are considered as weak acids. But among each other, the nitrous acid is stronger. How did we know that it's stronger? Because the Ka value is larger. When the Ka value is larger, this means that the dissociated forms are larger than the undissociated forms. يعني the little purple ones اللي كانوا في الجراف يكونوا larger in the case of the nitrous acid. Is this something very clear or not? Before we move on, because now we're going to get into some calculations and things will get a little bit difficult. All right, so we are saying again that among weak acids, there are some of them are stronger than others. How can we decide which one is stronger? Based on the Ka value. The higher the Ka value, the stronger the acid among the weak acids. So the example that we gave you was good enough to explain that. Now we're going to come to other issue, which is looking at some of the values, Ka values for weak acids that are multiprotic. Yani we have more than one H. If you remember in chapter 6 last semester, we talked about something called ionization energy. And we said that the second ionization energy is larger than the first one. The same thing over here. Removing, for example, if you consider oxalic acid. Oxalic acid has 2 hydrogens that are ionizable. In the first reaction, we lose one and we make a negative. That is, has a Ka value, all right? And the second one has another Ka value. Now look at the Ka1 and Ka2. Ka1 is times 10 to the minus 2, while Ka2 is 10 to the minus 5, which is much smaller. That means that removing another hydrogen from something that already has a negative charge will be difficult. That's why the Ka2 or Ka3 usually are smaller than the Ka1. As we lose more hydrogens, it will become more difficult to remove the remaining of the hydrogen. If you consider, for example, phosphoric acid, removing the first hydrogen or the first ionization, the Ka value is 7.5 times 10 to the minus 3. That's a weak acid, but has a value. Now moving to the second one, which is taking hydrogen phosphate or dihydrogen phosphate and lose another hydrogen in the second reaction, the Ka value is 6.2 times 10 to the minus 8, which is very, very small. Now compare the third one is even worse, because also removing the third hydrogen will become difficult. Okay, so that's that's what we want you to understand from this. table over here that Ka values for the same acid, multiprotic acid, will get smaller as we remove more hydrogens from there. Okay, some acids have more than one dissociating constant. We already said about that. Oxalic acid is diprotic, and we explained that already. Now, the Ka decreases from the first to the second, as you can see. We already said that. If you look at the oxalic acid over here, the first one is 5.6 times 10 to the minus 2. The second one is 10 to the minus 5. That's the most important part. And that is, I can guarantee you from now that there will be a question in any common exam that involves chapter 9 and 19 on this thing, is how to calculate the Ka value. Okay, now remember that the Ka value is equal to the two little purple one and pink ones in the graph, the second graph, divided by the shorter green, which is after dissociation. So what you need to know is a couple of things. You need two things. You can calculate the Ka. You need to know the initial concentration of that, of the acid, and you need to know the pH. Why we need the pH? Because, or the H plus concentration, either way. If you have the H plus concentration, or if you have the pH, either way, you can determine the H plus, right? Because if it is given, that's fine. If it is given the pH, you can do antilog of the pH, and that will give you the value of the concentration of H plus, right? So what we have, let me try to write again. This is Ka value is equal to the concentration of H plus times the A minus divided by the equilibrium concentration of HA. لما أقول equilibrium concentration of HA, I mean in the graph, if you still remember, we have a green over here, then we have another shorter green, then two little purple ones. These two little purple ones are the H plus and the A minus. The shorter green is the equilibrium concentration, which is after the ionization. How would I calculate this one? Remember that whatever shorter gets, it is exactly the same as the H plus, right? خلينا أخذكم على الفقر كمان مرة لأنه I know that you may be not with me on that, but let me explain it again. Here, okay? Now, if you take, just hold this A minus and put it over here, it will fit exactly in there, which means that the equilibrium concentration, this little green, is equal to the initial minus one of those, right? Is equal to this one. Let's call it the big green is equal to the short green plus this one. Or in other words, we can say that I'm interested in the short green. That is my equilibrium concentration of the acid. Then my equilibrium, the short green, is equal to the big green minus one of those, right? So in that case, so I'm going to write Ka again is equal to the H plus times A minus. Now you agree with me that H plus and A minus are equal. So if I give you the pH or I give you the H plus, these are the same. So H plus and A minus are the same. So that we get it from the pH. And the remaining, which is the equilibrium concentration of HA, that one, the green, short green, is equal to the big green minus one of those, which is the H plus in that case. All right. So again, what you need in order to calculate the Ka value, you need the initial concentration of the acid, the big green. You need the pH or the H plus in order to get the little purples. Then you can do your calculation and determine the Ka value. Now, instead of keep talking like that, we're going to take an example. In other words, here's the equation that we're talking about. Ka is equal to H plus times A minus divided by the equilibrium concentration. Remember that this one is an equilibrium concentration. It's not an initial one. And it is equal to the initial minus one of those, right? So if we move on to this question, all right, let's take a look at this question. In a 0.1 molar solution of ethanoic acid. So what is this 0.1 molar? This is your initial concentration. We start with 0.1 molar. Then we measure the H plus concentration and found it to be 1.34 times 10 to the 3 molar. He's asking you to calculate the Ka value of this acid. Refer to the table of ionization equation for ethanoic acid. يعني خلينا نشوف شو نسوي. Then what we're going to say is a Ka value is equal to the H plus again times A minus divided by the equilibrium concentration of HA. All right. So what is the H plus concentration here? It is provided 1.3 times 10 to the minus 3. What about the A minus? No. It's the same. Come on. مش the two little purples, واحد purple, واحد pink, they were equal. إذن هذا is the same as A minus as H plus also. So that is given. Now we come to this guy, اللي هو short green, is equal to the big green, اللي هو 0.1, minus any of them, minus one of the purples. So 0.1 minus this one is going to give you the equilibrium concentration. You substitute and you get the answer. يعني like that. خليني move back to the computer again. All right, so the ethanoic acid initial concentration is 0.1. The H plus is that. What is the Ka value? The H plus and the CH3O minus are equal. These are the two little purple ones. Time and remember the figure. That will help you to understand. Okay. Now, also, here's the table that will make it easy for you. The equilibrium concentration is equal to 0.1, which is the initial, minus one of those, either this one or that one. So initially, when we start, before we add anything, we have the concentration of CH3 initial was 0.1. What was the H? 0. What was the CO minus 0? We run the ionization, the change occurs. So this will lose some. This is now moving from this one into this one. This is the big green, and that is the short green. Okay? What is these? These are the little purples. Okay? So if you substitute those in the equation, as we said, then in that case, what you will have is the following. Yes. 1.34 times 10 to the minus 3 times 1.3 times 34, because they are similar. The initial, equilibrium concentration is not 0.1, it is 0.0987, which is after subtracting one of the, يعني هذا كمان مرة. I want to make sure that you guys understand this one. This one here is the short degree, or the short degree. The tall green, the one on the left, is the initial. We are interested in the equilibrium. All right. Now, in the next slide, I have a question that we usually have in the exams, which is, as usual, going to be twisted. Now, let's explain to you how it is twisted. Okay, this is a real exam question. Let's read. What is? It's not asking for Ka, it's providing the Ka, but asking you for the hydronium ion concentration, which is H plus. I'm بسألك عن H plus of 0.1 molar hydrochloric acid in solution if the Ka for that one is equal to 3.5 minus. Equation for the dissociation has. All right. So which one is the correct answer? You have to do the following. First of all, you have to write the equation as usual. Ka value. مع الكتابة هاي والله مشكلة. خلينا نحاول نحل المشكلة. نعم. مفهوم؟ أكيد. Is that clear, guys? هنشوف شو هذا. بيقول لا. Okay, that's the previous question. Very good, yeah. طيب. خلينا لا بس استنى شوي انا المره فاتت ها لا ما راح احط فيه راح اعمل شغل Okay, good. So K value is equal to the, in this case, it's going to be H3O plus times the concentration of C2 minus divided by the equilibrium concentration of HOC. Here, do we have only the initial concentration? And we have the Ka value. So this Ka value is provided. Then in that case, we have to assume that the H plus is equal to X. So H plus is equal to X, assume. So what we have, the Ka value then is equal to X, that is H plus, times what? Times another X. ليش؟ لأن هذول they are equal. We agreed on that. These are the two little purple ones. Where's the mobile? That's my Okay, so this is an X and that is an X divided by, what is the equilibrium concentration usually is? It is the initial minus X. Well, K value is equal to 3.5 times 10 to the minus 8. All what you need to do is to solve for X. مظبوط؟ هذا بيساوي X square divided by 0.1 minus X. If you do solve for X, which is going to be a little bit difficult, why? Because that will have two values. Solving what they call it, this second degree equation or quadratic equation, I don't know what they call it in math, but regardless, the only way that you can solve this question is by assuming one thing. And that one thing is consider that the amount of dissociation is very low to the point that you can ignore it. Yeah, in other words, we're going to ignore this X. Ignore this is like it is, has a very small negligible value. That is the only way. So if that is the case, then our equation becomes نضطر نمسح شيء أو بكتبه هنا. Our equation becomes 3.5 times 10 to the minus 8 equal x squared divided by 0.1. بطل في x هون. هلا بالعكس يصير العملية سهلة. يعني هاي بنشيلها من هون نضربها في 0.1 بعدين بنشيل السكوير بنعمل square root of. If you do that, this is the answer that you get. Okay, then one of those examples يا اما the previous one or this one will be in your exam. ما في فايدة. ايش؟ ايوه, either we ask you to calculate the K, and in that case we'll provide you with the initial concentration and the pH or the H plus, either of them, or we can give you the K value and the initial concentration, and you have to do this kind of thing, assuming that X is negligible over here. That's the only way you can solve this question. Okay, so these are the two possibilities. In the homework that is coming for chapter 19, there will be some examples in both scenarios. In addition to that, if يعني time permits, whenever we're going to have the third midterm, maybe we can do a review homework. Speaking of the review homework for the current exam, we prepared 15 questions. Listen to me carefully because this is very important. We have prepared 15 questions for you that are similar to your exam, which is going to be next Tuesday. All right. We're going to give you that as a homework, but it will be a timed, fixed on time and fixed in the duration. We're going to give you 50 minutes on Friday at 6 p.m. So assume that you have an exam that is online, although it's not an exam, it's a quiz or it's a homework. All right. So that quiz or homework or whatever you want to call it will occur on the Moodle exactly at 6 and will finish at 6:50. So you have 50 minutes. If you want really to benefit from that, what you need to do is to study like you are ready for the exam or kind of ready, and then you do it without looking at anything. Just try the timing and try your ability, see your gaps, see where you are missing something. Whatever missing, you can fix it in the coming days. You still have Saturday, Sunday, and Monday before the exam. So let's say, for example, there was a question about Boy's law that you could not solve. Then this means that you still have problems with Boy's law. Go back and review it. All right. Don't worry too much about the grade as much as worry about testing yourself. So you are testing. Don't do the test if you're not ready. If you didn't study before Friday at 6 p.m., then it's useless because at that time you will be going there just to have fun or somebody to give you the numbers. You have to study first and test yourself. So that is a test for you, not for us. But it will give us some information about the time. And that's why it is important that you do this by yourself and you do it the right way, which is without any help. Okay? Yeah, Judy, this is not a right question. Yeah, to study part of the exam, you have to study for the exam. And for the exam, you need to study chapter 12, 14, and 17. All of these are included in the exam. So you have to study all of them before you attempt this homework. That is one announcement. The second announcement, if you go to the Moodle now, you will find a report sheet for the coming lab, which is going to be Thursday. This Thursday, we have a lab. And also the assignment for you to submit your lab report. Now, in the past reports, I've been nice enough to forgive people who submitted late by a couple of hours. But this time, that's it. I دلعناكم 3 times, that's it. This time, either you submit it on time before 11:59, or you are not going to get grade for the whole thing. You're going to get 50%. So for those who did submit it late last time and the time before, this was just a gift for you. Now ما في مسامحة في الموضوع. خلاص 3 times is more than enough. And for those who do not attend the lab, please do not submit the lab report, because I told you from the beginning that if you don't attend the lab, you're going to get a 0, and that's it. So don't submit the lab report and then send me an email. What's wrong with my lab report? Why are you giving me a 0? I mean, you know why. Why are you asking such a question? If you don't attend, don't submit. But if you attend and you forget to submit or you late in submit, you're going to get 50% of the grade. I am very clear about this. So you know what to do. You need to attend the lab, fill up the sheet, submit it on time from 11 a.m. in the morning till 11:59 p.m. in the night on Thursday. Clear? All right. طيب خلينا to move on with the lecture then. I decided to do this announcement during the lecture so you guys have a recording of this. حد يقول لي انه ما فيش recording ولا. Okay. طيب. Now, base dissociation constant. Everything we said about acid applies to the bases. The same thing. We have a Kb value rather than Ka, K base. So the same thing applies to the base. A strong base dissociate completely into ions and hydroxide ion. The weak base, the one which will dissociate or will ionize partially, a weak base will, and for weak bases, we can differentiate between them by using the Kb value, and it is calculated the same way. Okay, so for example, if you consider ammonia as a weak base, when we put it in water, then it will be ammonium and hydroxide ion. Now remember that this ammonium, if you remember, according to the Bronsted and Lowry thing, we said that this is a base, this is what? A conjugate acid, and that is the conjugate base because of the acid, which is the water in that case. So if you do the equilibrium concentration, exactly like what we did in the acid, and OH minus is the low as equal as possible. So the K equilibrium is equal to the ammonium, the hydroxide, NH3, and if we move the water into this side to make it a Kb value, then the K equilibrium times the water is equal to Kb, and that is equal to the ammonium ion times the hydroxide ion divided by the equilibrium concentration of ammonia. These two, the ammonium and the hydroxide, they are the same. Remember that. H plus and A minus are the same. Here, NH4 plus and OH minus are also the same concentration after equilibrium. The equilibrium concentration of the ammonia over here is equal to the initial minus one of those, NH4 plus. Like what we did with acid. What we did with acid applies to the base 100%. So the base dissociation constant Kb is equal to the ratio of the concentration of the conjugate acid. Here he's using different terms, but that is the ammonium. Now we know that ammonium is a conjugate acid and the hydroxide ion is the conjugate base, but here he put and the equilibrium concentration of the base, which is the ammonia in that case, in the case of the ammonia, all right? The magnitude of Kb indicates the ability of a weak base to compete for a very strong hydroxide ion. It is the same thing. As the Kb value increases, then that is a stronger base than the one which is compared. So if we have two bases with two Kb values, the one with the higher Kb value will be stronger base than the other one. And for the strong bases, of course, we don't have a Kb value. These are for the weak bases usually. All right. So the Kb for ammonia, for example, is 1.8 times 10 to the minus 5, similar to the ethanoic acid Ka value. All right. The magnitude of the Kb indicates the ability to compete. We already said about that. And okay, the smaller the value of Kb, the weaker the base. And that's it. Okay. Now we're gonna do the last concept, and that is to differentiate between two concepts. One of them is known as the concentration, and the other one is the strength. شو الفرق بين هذا? That's why the Faisal Hussein, when you said more acidic at the beginning, I did not like that kind of answer. I prefer to say stronger acid rather than more acidic, because more acidic means more in the concentration. So what is the difference between the concentration and the strength? The concentration of how much material, how many moles you have per liter. That is different from, so we have either a concentrated or a diluted. If you have 10 molar, that is concentrated. If you have 0.1 molar, that is a dilute. But the fact that being strong or weak, that depends on the Kb value or the Ka value in the case of the acid. In other words, let me just give you another example over here. Consider the hydrochloric acid. What is HCl? Is a strong acid. Now, whether we have it at 12 molar or 0.8 molar, 0.8 molar hydrochloric acid, or the gastric juice, that is the one which is in your stomach, is 0.8. And this is the one which we prepare in the lab. This is concentrated and that's dilute, but both of them are strong. So being strong doesn't mean, has nothing to do with the concentration. That's what we're trying to say. Okay, so being strong has to do with the Ka value or the degree of ionization. That's why ethanoic acid or vinegar is the same as ethanoic acid. الخل في acetic acid. That's all what it is about. So vinegar and ethanoic acid is 17 molar concentrated, but still it's a weak. Now being also 0.2 molar is still a weak. So the weak and strong has to do with the type of acid, and the concentration has to do with how many moles we have per liter. Okay, so there's a difference between being concentrated and dilute and being strong and being weak. So that is something that is worth explaining. The gastric juice that you have in your stomach, of course, it is a strong acid, which means that it will dissociate 100%, but it is very dilute. Because it is dilute and because your stomach has a wall that is protected against acid, nothing is going to happen to your stomach. But when you have what they call it, disease, when you have a ايش سموه الارتجاع هذا I forgot. لما يكون عندك acidity حموضه في معدتك it will go back into your esophagus over here, so بتصير تحس بألم. ليش؟ لأنه your stomach is built up in a way that to absorb or to protect against the acids. That's why nothing is going to happen. But when the acid goes back into your esophagus here up to your throat, that will hurt because that is not made to work with strong acids like that. So anyways, the gastric juice in your stomach is a dilute solution of the hydrochloric acid. Even when the concentrated hydrochloric acid is diluted with water, it is still considered as strong acid. That's the point here. Even with high concentration, ethanoic acid still as then we go back to the original question, why the citric acid is safe to digest, although the pH is very low, because it is a weak acid originally, because it's a weak acid, and also it is a multi-product. So the question is, what does this mean to you when we have citric acid has 3 Ka values? What does that mean to you? When we have an acid that has 3 Ka values, this means that it is what? Triprotic acid. That's what it is. So citric acid, as a matter of fact, has this kind of structure. So you can see here that this is one acid part, or this is hydrogen. This hydrogen is part of another carboxylic acid and these. So 1, 2, 3. This one, no, because this is an alcohol. So 1, 2, 3 ionizable hydrogen with 3 Ka values. So each Ka value belongs to one of those H plus that are there. It is a triprotic and it is safe because it is a weak acid. The same concept of weak and strong and concentrated applies to the bases, the same thing. In strong acid or ionizable hydrogens completely ionized, in weak acid شو بيكونوا partially ionized. مظبوط? That is the conclusion. In strong acid, all ionizable hydrogen are completely ionized, and in weak acid, it is partially ionized. That is something we agreed upon, and that is the end of the section. Okay, I'm sorry I took 2 minutes of your time, but that is because of the strength depends on the Kb and Ka, that is true, and the concentration depends on the number of moles, which has nothing to do with the strength. All right, any questions or concerns or anything? So Thursday we're going to have a lab. The sheet is already there in the Moodle. The assignment is there for you. Since I'm not going to see you Thursday, then Friday at 6 p.m. I will put it today, the review homework. It will open at 6 and will close at 6:50. Please do it the right way. Okay? Anything? All right. So we can. All right. We'll speak to you then on Sunday.